Oh, how dare you take the land of my people, my ancestors, my homeland. I will make you pay by taking your intelligence.
You wouldn't dare. This land, it's mine. I'll beat you with my incredible trigonometry skills.
Oh! Ha, you act like I've been training for this my whole life, but I in my time going from rags to riches.
You fool, I have the power of the IDF and America on my side. I'll destroy you. Get ready to be crushed by the power of verifying identity.
So when verifying, what we're going to do is we're going to plug in x values or certain angles into each side of the equation. So first we're going to take the left hand side and we're going to plug in pi over 6. So we get cosecant pi over 6 sine pi over 6 over cosine pi over 6. And that gives us 2 times half over square root 3 over 2. And then we rationalize that by multiplying 2 over square root 3 times square root 3 over square root 3. And then we get 2 square root 3 over 3. Then we do the same for the right hand side. So we get secant pi over 6, and that gives us 1 over square root 3 over 2. We rationalize that, multiplying it by square root 3 over square root 3, and we get 2 square root 3 over 3. Then we have to do the same thing, but with an angle in degrees. So we have cosecant 60 times sine 60 over cosine 60. That gives us 2 square root 3 times square root 3 over 2, divided by 1/2, which then ends up giving us 2. Then when we do the right hand side, we have secant 60, which is going to be 1 over 1/2, which also gives us 2. So because the left hand side equals the right hand side, we can say that it's verified for x equals 60, and it's verified for x equals pi over 6.
Your verification isn't powerful enough, not against my trigonometric proof.
So, we're going to prove an identity and show the MPVs. So, at the top or left corner, we have the identity. Sine to alpha is equal to 2 sine alpha cos alpha. So we're going to prove that. We're going to show that this really works. So we're going to split it up onto left-hand side and right-hand side. So on the left-hand side, we're going to work around with the sine to alpha. And what we're going to do is we're going to kind of expand that angle. So 2 alpha can also be written as alpha plus alpha. And what this allows us to do is it allows us to use another trigonometric identity as shown below. That sine alpha plus beta is equal to sine alpha cos beta plus sine alpha cos beta. And what we're going to do is we're going to plug in that identity to move things around, right? We're going to see how it's going to work out. So we're going to plug that in, and our resulting in our original identity is sine alpha cos alpha plus cos alpha sine alpha, as shown underlined by the purple marker crayon. Well, this can also, since both terms are alike, we can combine them and we can get 2 sine alpha and cos alpha. And would you take a look at that? That's equivalent to the right hand side of 2 sine alpha cos alpha. And as the left hand side is equivalent to the right hand side algebraically, it is therefore proven. Now, what I like about proving identities compared to verifying them is that proving them really lets you show and confirm that this solution, this identity is applicable for any value. Verifying only allows you to confirm a solution for a specific value. Meanwhile, this proof verifies that any given value that is within the restrictions it will end up working. Now, let's take a look at our MPVs. Well, as you can see, we have none because we don't have any fractional or any trigonometric restrictions. It's a simple term by term, no fractions, so we don't have any MPVs to worry about, and therefore there are none.
Oh yeah? We'll take this graphical solution of a trigonometric equation.
Oh.
I'm going to solve 2 cos theta equals square root 2 graphically. The domain is theta is less than or equal to 2 pi and greater than or equal to 0. The answer is going to be in an approximate value. So if I subtract square root 2 on both sides, I'm going to get 2 cos theta minus square root 2 is going to equal to 0. If I plug that in the calculator and find the zeros, I get 0.785 and 5.498.
Does your intelligence only go to approximation? Well, get a load of my general solution.
Alright, so next we're going to be determining the general solution using technology. So what we have here, is we have the basic equation, and what we're going to do is we're going to move it around to be able to input it into a graphing calculator. So that results us with f of theta is equal to 2 sine theta minus 1. Now we're going to input that into our graphing calculator, let it do the work, and we have our identify the first two solutions. These solutions are then to be, as seen by the graph, going to be repeated over and over again every circle. So our solutions, in order to make a general solution, we need to set up an infinite loop, cycle that'll keep going. But first of all, let's take a look at the two solutions on a unit circle. And as you can see, Cartesian plane. As you can see on the Cartesian plane to the right, the two solutions don't really align in a way that is really symmetrical in any way. So we cannot create a loop that allows us to have sequences that allow us to match up with every solution. What that means is that they won't ever line up, and we need to create two separate solutions in order to identify loops for both of them. So as seen below, we're going to have that general solution. Theta is equal to the start initial bounce, pi over 6, or 5 pi over 6, and then plus 2 pi, signifying the period of each change rotation, 2 pi n, n being the amount of rotations, and n has to be an element of an integer.
But can you do it algebraically?
So I'm gonna solve 1 over square root 3 tan theta equals 1 algebraically, and that the domain is going to be theta is less than 2 pi and greater than 0. So if we multiply by square root 3 on both sides, we're going to get tan theta equals square root 3, and tan theta is also sine theta over cos theta, and sine theta over cos theta. To give us square root 3, we're going to have to, sine is going to have to be square root 3 over 2, and cos is going to have to be 1 over 2. So given that information, we can find theta on the unit circle, and we get that it's pi over 3 and 4 pi over 3.
I see your weakness in general solutions. It seems you are no match for my infinite range.
Next, we're going to take a look at doing a general solution of the trigonometric equation, and we're going to do it algebraically. So first we have this equation up at the top, starred by the blue star. And what we're going to do to solve it algebraically is we need to identify the x-intercepts. How we're going to do that is we're going to plug in 0 for the y value, or known as f of theta, and from there on we get ourselves an equation that allows us to factor it nicely. The way I like to factor is by splitting the first term and the last term, and to make sure that they add up, multiply and add up to give us the middle term. What I mean is, if we take a look at this example here, we can see 10 sine squared theta can split up into 5 sine theta and 2 sine theta. If you multiply those together, you get back to the 10 sine squared theta, right? On the other hand side, we have the negative 3, and we can split that up into negative 3 and 1, because negative 3 times 1 is negative 3. So it works out. And now what we're going to do is we're going to cross multiply. What that means is that we're going to take 5 sine theta multiplied by 1, which remains the same, 2 sine theta multiplied by negative 3, which gives us negative sine theta, and we're going to add those products together, and that's going to produce negative sine theta. And when you take a look at that, as highlighted by the red crayon, we see that those middle terms are equal with one another. Therefore, this factoring process is correct and accurate. So, as you can see, we have the two factors, and we're going to take a look at them individually equivalent to 0, as that is our original equivalency, right? What we're going to do, we're going to work around to get sine theta equals 3/5, sine theta equals negative 1/2. Then we're going to take a look at the unit circle, identify all the angles and the coterminal angles that fit within the unit circle, making sure that we are within the restrictions. What I mean by this is that if we take a look at, for example, sine theta equals 3/5, we have to make sure that it is within a positive range on the unit circle. Sine theta equals negative 1/2, pardon me, has to be within the negative y value. We take a look and we get our solutions of 37 degrees, 143 degrees, 210 degrees, 330 degrees. And in the end, what we have to do to identify a general solution is we have to take this starting angle and just add 360 degrees. Unfortunately, none of the angles align with each other in a symmetrical sort of fashion, so all of them need to have their own general solution. And as mentioned, we have the initial, and we add on the 360 degrees n, showing that for however many turns, we need to add 360 degrees to loop back to the to a coterminal angle of that exact value. N is an element of the integers, meaning that it has to be an integer value that depends on how many rotations you're doing. 1 rotation, 2 rotation, however you like.
You could never beat my exact value ratio using a sum identity. This will eviscerate you.
Now I'm going to find the exact value ratio for cos 9 pi over 3 using sum identity. So cos 9 pi over 3 can be written as cos 4 pi over 3 plus 5 pi over 3. So then if we use the sum identity, we get cos 4 pi over 3 times cos 5 pi over 3 minus sine 4 pi over 3 times sine 5 pi over 3. And that's going to give us negative half times half minus negative square root 3 over 2 times negative square root 3 over 2. So that's going to give us negative 1 over 4 minus 3 over 4. And that's going to give us negative 4 over 4, which gives us negative 1.
All my internal organs have been destroyed. No matter, it's time for me to regain my health and graphically verify trig identity.
Next, we have graphing an identity to potentially validate it. What this allows us to do is it allows us to see whether this identity has a potential to work. If we can graph both sides of an equation and they line up, then there's a good chance that they will end up working for any value. However, this does not confirm it, as a proof requires algebraic determination and determination of MPVs, which is not intuitively shown by a graph. So this is just potentially validating. Anyways, so what we do is we have the identity highlighted by the blue star, and we're gonna split that up into 2 separate functions, graph that into the function, and as seen is in the Desmos graph, that they line up perfectly. So they're both lining up perfectly. So this really shows that there's a good chance this identity really works. However, once again, we need proofs for mathematical confirmation.
You will never be able to even walk after you take some of this trig ratio using a difference identity.
Oh!
And now I'm going to solve for the exact value ratio for tan 75 degrees. And I'm going to do that using the difference identity. So tan 75 degrees can also be written as tan 135 degrees minus 60 degrees. And that's going to be tan 135 degrees minus tan 60 degrees over 1 plus tan 135 degrees times tan 60 degrees. So tan 135 degrees is negative 1. Tan 60 is 2 times square root 3 over 2. We subtract that over 1 plus tan negative 1 times 2 times square root 3 over 2. And that's going to give us negative 1 minus 2 square root 3 over 2 over 1 minus 2 square root 3 over 2. So if we rewrite the negative 1 and the 1 as negative 2 over 2 and 2 over 2, we can get both the numerator and the denominator to all have denominators of 2, and then we can get rid of those denominators and we get a negative 2 minus 2 square root 3 over 2 minus 2 square root 3, and then if we divide that by 2, we're going to get negative 1 minus square root 3 over 1 minus square root 3. Multiply that by 1 plus square root 3 over 1 plus square root 3, and then we're going to get negative 1 minus square root 3 minus square root 3 minus 3 because we multiplied it. And on the bottom, we're going to get 1 minus 3. So on the numerator, we're going to get minus 4 minus 2 square root 3. And that's going to be over negative 2. And at the end, when we divide it by negative 2, we're going to get 2 plus square root 3.
This doesn't seem to be going too well. It's like the end. But I must hang on. I must fight for my people. It's time I use some verification.
Next, we're going to be verifying a trig equation. And what we're doing here is we have our trig equation as shown in the blue. And what we're doing is that we need to verify for this trig equation when theta is equivalent to 210. Well, what we can do, there's 2 ways we can do it. You can either just directly input it into theta or move things around as you like. I like to move things around because it makes things simpler for me, because then the whole equation equals 0. So if I get a value of 0, I know I'm doing something right. So what I did is I moved it around, then I inputted theta as circled by the purple crayon, and then I input and calculate the values, and I get a value of 0. 0 equals 0, it's verified. Now, please note that verification of trigonometric equations are different from identities, as identities hold true for all circumstances under restrictions, while functions are equations used for identifying characteristics and such, and may not be applicable in other problems for substitution.
This is it. After this, I will be the supreme leader of this land. Take this!
Now I'm going to find the exact value ratio for sine 14 pi over 4 using the double angle identity. So sine 14 pi over 4 can be written as sine 7 pi over 4 plus 7 pi over 4. If you're using the double angle identities, that's going to turn into 2 sine 7 pi over 4 times cos pi over 4, 7 pi over 4. And then sine 7 pi over 4 is negative square root 2 over 2. And cos 7 pi over 4 is square root 2 over 2. So if we multiply that by 2, we're going to get 2 times negative 2 over 4, and negative 2 over 4 is also negative 1 over 2, so then at the end we're going to get negative 1.
So, I recommend your strength, but have you forgotten your past? So I've dug up an old algebraic equation you must solve incorrectly. It is time, for I've been biding my strength to use my ultimate reversal move, identifying and correcting errors.
Next, we have identifying and correct errors in solution in a solve. Next, we have an identifying and correcting errors in algebraic solve. So here we have the question at hand. If 2 sine squared theta is equivalent to sine theta and theta is greater than 0 but equal to then or less than pi, find theta. Here we have Sonia's algebraic solve, and as you can see here to the left, she has completed the steps by first of all removing by dividing out a sine theta, and that produces her theta result. However, the issue with this solve is in step 1 that she actually eliminates a sine theta. What that does is it removes a solution as highlighted to the top right. So what we need to do in order to maintain and preserve all the solutions is we need to actually factor as shown at the bottom left of this solution, and we pull out sine theta, so we get sine theta multiplied by 2 sine theta minus 1 is equal to 0. Now we have it factored. Take a look at each individual factor, work around to find theta, and theta is equal to pi over 6, 5 pi over 6, and pi that fit within the domain as mentioned above.
This land shall be yours. Israel is
Finally, it's over. Jerusalem's ours. My brothers and sisters are free. We can once again take our place in Jerusalem.